Hi everyone, today I'm going to do an introduction to trig identities. So if you have no experience proving trig identities, this is a great lesson to get you started. So firstly, we need to know what an identity is. And an identity is basically going to be an equivalent expression that is true for all values of the variables in that expression. So I'm going to take you to a little example that shows us the difference between an equation and an identity. So here's a really great example. On the left, we have an equation, and basically the difference between this equation and what I have over on the right, which is an identity, is that the equation on the left is actually only true for some values of x. Whereas the identity on the right is actually true for any value of x. So if I calculated the cosecant of 50 and I calculated 1 over the sine of 50, this would be a true statement. If I chose a different x, let's say I choose 27 degrees and I calculate cosecant of 27, that's actually going to always be equal to 1 over the sine of 27. But we know that on the left here, I can't just plug in anything that I want for x. This is actually only true for some very specific values of x, which I actually have to solve for. So like I said, an equation has to actually be solved, and it's only going to be true for some specific values of x. And our identity on the right, it doesn't need to be solved. It's simply an equivalent expression, and it's true for all values of x, no matter what value of x I choose. So now that you know the difference between an equation and an identity, we're going to move forward to some other important information to know before we actually get into proving trig identities. So the way that I'm going to have you guys set up your proofs is you're going to set up a left side and right side. We're going to draw a line underneath, and you're literally going to copy the left side of the equation, or rather the expression. And then on the right side, you're going to copy the right side of the expression. So whatever is on the right side of the equal sign. Okay, now that you've done that, then we're going to do some work with some trig identities. So I'm going to introduce to you guys a couple trig identities in a second. For my class, I've posted up a little sheet for you that you need to have on hand. But if you're watching this video and you're not in my class, don't worry, we're going to get to that point. So basically we're going to do some work, and our goal in this proof is to make the left side look exactly like the right side. So I can work on the left side and I can work on the right side, but my goal here is that they're exactly the same by the end of the work that I've done. So we're going to do some work, and anytime that I start a new line, I'm making sure that I'm writing equal signs over here, and same thing on the right side. So maybe I'll do 2 lines here, and again making sure that I draw equal signs after that. And ideally what I want at the end is an expression here that's exactly the same as my ending expression on the right side. And if I have that, then my proof is done. So what I'll write at the end here is left side equals right side, which is the most important part. And then sometimes we as mathematicians end off proofs in a couple of different ways. So you have a couple options. I usually like to just write a box, and that's just like our little mathematical brag saying like, oh, we've squared it away. Sometimes the box is also solid, filled in. So if you want to do that, you can. Or a lot of mathematicians end off their proofs with a short form of a Latin phrase, which is QED. So in my very poor Latin here, it's quanto ero demonstratum, and it basically just means which was proven above, or which was demonstrated above. Okay, so either one of those two things, you're going to see me using the little box. But if you like to put QED because you want to be fancy with your Latin, you can do that as well. All right, the other thing that you're going to want to have on hand while we do this lesson is this set of fundamental trig identities. So because we're doing just a brief intro here, I'm not going to get into a lot of the stuff that we get into with our grade 12 identities, but these are basically like our standard grade 11 identities that we're going to work with. So if you're in my class, hopefully you have already copied this out or you have it printed out. If you're not in my class, or if you haven't copied it or printed it, I would say take a second and pause the video and get this copied out on a sheet of paper that you can have in front of you while you try some of these examples. I'm also just going to go through a quick list of tips and tricks that will help you when you're proving trig identities. And whenever you get stuck, I would say look back at this list and hopefully it will help you. So the first tip, and probably one of the most important tips, is that you get everything in terms of sine and cosine when you're trying to prove trig identities. We have a lot of different trig ratios. We have the secondary trig ratios, we have the primary trig ratios, and if we have 6 different trig ratios floating around all at one time, it's going to be really tough for us to make the left side equal the right side. So I would say 90 to 95% of the time, this is how you're going to start all of your proofs, is get everything in terms of sine and cosine. The second tip is that you want to be aware that you can actually square the left and right sides of your reciprocal and quotient identities. So if we look back at what the quotient and reciprocal identities are, they're simply one term equals another term for both reciprocal and quotient. So I can definitely square one side and square the other side, and that equation will still hold true. Or sorry, I should say that expression will still hold true. So let's take an example. Let's say we look at cosecant equals 1 over sine x, and I'm also going to take a look at tan x equals sine x over cos x. So for the first one, cosecant equals 1 over sine. If I square both sides of this, because they're both single terms, I can simply just square the left side. I'll get cosecant squared x. And I'll square the top and bottom of this fraction. So 1 squared is 1, and sine x squared is sine squared x. Now, one really important thing that we really touched on super briefly on a previous worksheet is that sine squared x actually means sine x times sine x. And this technically is another way of writing sine x all squared. Now, the reason why we don't simply just write it like this is that it gets a little bit confusing as to whether we're squaring just the x or whether we want to square the entire sine x. So in order to make sure that we don't have any confusion, if I want to say the entire sine x squared, I write the squared between sine and the x rather than at the end. So we're always going to express sine x times sine x as sine squared x. Okay, so you can see here that our equation is still equivalent because I've done to one side what I've done to the other side, or should I say expression. And the same thing goes for the remainder of the reciprocal identities and also both of the quotient identities. So for instance, we have a quotient identity, which is sine x over cos x is equal to tan x. And I can do the same thing here. So I can square the left side and square the right side. And that means that tan squared x is actually equal to sine squared x over cos squared x. Okay, this one we use a lot in our proving. So I would say maybe that one would be a good one to add to your identities sheet. And if you wanted to, you could also add one of these or just make yourself a note on your trig identity sheet that you can do this with all reciprocal and all quotient identities. Okay, so I've added just a little note for myself that I can square both sides of both of these identities, and I've added the 2 examples that I wrote on the lesson. So if you have your trig identity sheet or you have it copied out, this is going to kind of be like your little guide throughout the next few days when we're doing trig identities. So make sure you keep it on you and make sure you add the things that I've asked you to add on here. So this also extends to secant and cotangent. So secant squared is equal to 1 over cos squared, cotangent is equal to 1 over tan squared, and in the middle here, cotangent squared is equal to cos squared over sine squared. Let's go to our next tip. All right, our next tip is similar to our second tip, but this one's a little bit different. The tip is to rearrange your Pythagorean identities by moving terms to the other side of the equal sign. So I'm going to use the first Pythagorean identity as an example here. Sine squared plus cos squared equals 1. This is probably the one that we use the most out of these three Pythagorean identities. So I can't really square both sides here. I mean, I can, but it doesn't really help me with anything because I can't. In order to do this, I'd actually have to like multiply it by itself and FOIL it out. So yeah, that's technically still true, but it doesn't really help us rearrange in any useful way. But I can take cos squared x, for instance, and actually move it to the opposite side of the equal sign. So when I do that, I get that sine squared x is actually equal to 1 minus cos squared x. And if we imagine keeping the cos squared x and actually moving the sine squared x instead, I would get a second rearranged version of this, which would say that cos squared x is actually equal to 1 minus sine squared x. So I'm going to ask you to add that to your fundamental trig identity sheet as well. And also just be aware that you can move the remaining Pythagorean identities. You can move any of those terms to the opposite side of the equal sign as well. Okay, but these two that I've asked you to add here are the most important ones. And I would say we even use these rearranged versions more than we use the original sine squared plus cos squared equals 1 version. Our next little tip and trick is to look out for difference of squares. So I just want to give you a regular example of difference of squares, just so that we can think back to what we already know. So if I have something where I have two terms that are perfect squares that are being subtracted, I can actually factor this into the sum and difference of their squares being multiplied. So x plus 4, x minus 4. This is a way that we can factor x squared minus 16. And similarly, if I FOIL x plus 4 times x minus 4, I'll get back out x squared minus 16. So those two rearranged versions that I just showed you of our Pythagorean identities, 1 minus sine squared x, this is actually an example of a difference of squares. 1 is a perfect square, and sine squared is, of course, a perfect square, and they're being subtracted. So I can actually factor this into 1 plus sine x and 1 minus sine x. Same thing goes for 1 minus cos squared x. We can factor this into 1 plus cos x, 1 minus cos x. So that's an important way that we can use difference of squares. You may also see something like, if you happen to see cos squared x minus sine squared x, this can actually be factored into cos x plus sine x and cos x minus sine x. So same math rules and factoring rules that we have learned in the past apply to trig identities. Also, I can use these all in reverse. So if I have something like this, it FOILs out into this expression. So I may need to use these by factoring, but I may also need to FOIL these and use them in reverse to get these guys back. So whatever helps us is kind of what we'll use in our proof questions. Another tip here is to use power rule. So again, I want to draw on some previous knowledge here. And that previous knowledge is that if I have x squared cubed, I have a power on a power. That means I multiply my two exponents together. So I'm going to kind of use this rule, but in reverse. So let's say we get an example that uses something like sine to the exponent 6 of x. Now, I don't really have many trig identities that can be useful in a format like this, but if I were to express this as sine squared cubed, it's still equal to sine to the exponent 6, but I've just expressed it in a different way using power rule so that I have a sine squared. You know that looking at our trig identity sheet here, we have sine squareds here, we also have sine squareds here. So it's a lot more helpful to have sine squareds rather than sine to the exponent 6. And finally, when you have two or more fractions that are being added or subtracted, I would say a very good move that you could do would be to find a common denominator and put those fractions together, especially if you notice that one side of your proof doesn't have multiple fractions. So I would say this would be the way to go most of the time. All right, so if you ever get confused, we want to look back at these tips and tricks and try to employ some of these techniques. We're also going to make sure as we get into doing some of these proofs that we have this in front of us and available, and I'll also flip back and forth between it as well so you can see which of these fundamental trig identities I'm going to be using in our questions. So without further ado, let's try an example. All right, so this one's kind of already set up as far as left side and right side for us. So basically what you want to do is copy out your left side of the equal sign and copy out your right side of the equal sign. Now that we have that, we're going to use our number one tip, which is try to get everything in terms of cosine and sine. Now, if you have something like a 1, like we have over here on the right-hand side, it's not necessary that we turn that in terms of sine and cosine, but if we have other identities, other trig ratios like tan, cosecant, secant, cotangent, let's try to get those in terms of sine and cosine. So I'm seeing one thing here which we could look at our trig identity sheet and see if we can find something that has sine and cosine rather than tan. So if you look through your identities here, can you find anything to do with tan x that has it expressed in terms of sine and cosine? If you found the one in the middle, which is tan x equals sine over cosine, you're right. That's what we're going to replace tan x with in our actual trig identity example here. So let's do that. So in place of tan x, I'm going to sub in its identity, which is sine x over cos x. Okay, so nothing fancy going on here. You know, when you know something is equal to something else, you can replace it with that thing. If I know x is equal to 2, I can sub that in. If I know tan x is equal to sine x over cos x on my sheet here, I can put sine x over cos x in place of tan x. Okay, so I'm just expressing this in a little bit of a different way. And remember that cos x is technically over 1 here. So I have a cos x on top being multiplied with a fraction where cos x is on the bottom. These can actually cancel. And all that I'll be left with here is sine x over sine x. And what's anything divided by itself? Well, 2 divided by 2 is 1. X divided by x is 1. So sine x divided by sine x must also be equal to 1. And you'll see here that now the left side and right side are actually equal. They're exactly the same. And that means that I've proven that the left side of this identity must be equal to the right side. And I'm gonna just end my proof with proper format here, saying left side equals right side, and end it with a box or QED. So that's a very basic example of what trig identities look like. If you ever get frustrated with these, this is a little bit different than the math that we're used to doing. We're used to always like solving for something, but in this case, we're actually given the answer. We already know that this is true. We're simply proving that it's true. And you'll notice if you're in my class, when you're doing some of your worksheets, that I actually have scribbled out parts of them because I just start something and I'm finding that it's not working for me, so then I try something else. There could be multiple different ways to do the same proof, so just be aware of that as you're doing your proofs, that not everyone is going to do the exact same approach for these. Let's try another one. So I'm simply just going to copy out my left side and copy out my right side onto their respective parts here. And you'll notice here that we're using theta rather than x, and all of our trig identities have x's. It doesn't matter what the variable is. It can be theta, it can be y, it can be x. If you feel more comfortable with x, go ahead and replace all those thetas with x's. But as long as we keep with the thetas, we'll be fine. So first things first, I think I'm going to start working on the left side here because it's a little bit more complex. Also, I'm noticing that there's a couple of trig ratios here that are not in terms of sine and cosine. So that's the first thing that I'm going to take care of. So sine is good because that's, of course, in terms of sine already. I want to look for something for secant and for cotangent that we could replace those with. That's in terms of sine and cosine. So let's look at our sheet. Look for one with secant to start. Do we have an identity with secant that's in terms of cosine? If you found this one, you're right. We're going to do 1 over cos x for that one. Now I want you to take a look for an identity involving cotangent. There's a couple of options here. I have an identity involving cotangent here, and I also have an identity involving cotangent here. So you need to decide which one is going to help us get this in terms of cos x and sin x. And if you guessed the second one, then you're right. We're going to use this one over here. I very rarely use this one, to be honest, especially when I'm employing this method of getting things in terms of sine and cosine, because this one's already in terms of sine and cosine. So I'm going to enter in 1 over cos x and cos x over sin x for secant and cotangent in our example. But in this case, we're using theta, so I'll replace those with thetas. Okay, and remember, this guy is technically over 1 here. So now I'm noticing I've got a bunch of fractions that are being multiplied. I have a cos on bottom and a cos on top, and I have a sine on bottom and a sine on top that I can cancel. And what I'm going to be left here with here is actually 1. And now I have left side equals right side. So a couple of things that you should be noticing and also doing in your proofs is that after I've written left side and right side, any line that I add after that has equal signs in front of it. I'm also leaving like a decent amount of space in between those just so that it doesn't get confusing. And I'm making sure that I really make sure that I kind of show all of my work here. I'm showing that this is being replaced with this. I'm showing that cotangent is being replaced with its identity, because we want to be very thorough with proofs. We are proving beyond the shadow of a doubt that this particular identity is true. So skipping steps in proofs is definitely something that we do not want to do. All right, let's try another example. We're going to copy out the left side, copy out the right side. And typically what I do is I look for the more complex looking side to start with. Sometimes also if I notice that there are trig ratios in there that aren't sines and cosines, I'll kind of start with that just so that I know that we have similar things on each side that we're kind of trying to simplify. So here, everything's in terms of cos x and sin x. So I'm going to start with the more complex side, which I think is the right side here, and we'll see where we can go. So you might be noticing already that the right side has a 1 minus sin x and a 1 plus sin x, which looks similar to something that we talked about in our tips and tricks section. So if we look here, we actually have this. And I know that this is a difference of squares. So if I FOIL it out, it's actually going to give me 1 minus sine squared x. So I'm going to go ahead and write that on my next line. And that is basically just from foiling this expression. So just really quickly here, if you want to see how this can be FOILed out and why it's equal to 1 minus sine squared x, we'll do distributive property. So first, I get 1 times 1 is 1. Outsides, 1 times sine is just sine. Insides, negative sine times 1 is negative sine. And lasts, sine x times sine x is sine squared x. And it's a negative times a positive, so it's negative. This is a plus, this is a minus. Those cancel each other out. That's equal to 0. And we're left with 1 minus sine squared x. So I don't need to see this whole foiling thing every time. I trust that you guys know how to FOIL. And I also don't need to see this. I'm just doing this for the purposes of our lesson right now. Okay, 1 minus sine squared x. Okay, I'm trying to head for something that is cos squared x. So when I'm kind of at the point where I'm stuck and I can't really simplify anything else, I look at my identity sheet. And my identity sheet, if I'm looking through, I'm looking for a 1 minus sine squared x, and I'm noticing it down here. This is actually one of the ones I asked you to add to your sheet. So 1 minus sine squared x is actually equal to cos squared x. So I can actually simply go in here and I can replace 1 minus sine x with, or sine squared x with cos squared x. Now, a lot of students ask me if they can use the identity on the left-hand side instead. Like, can I write out cos squared x equals 1 minus sine squared x? Because that's basically the identity as well. I can use it both ways. And the answer is yes, completely yes. If you want to work on the left-hand side and then say left side equals right side, or if you want to work and replace this on the right-hand side with cos squared x and say left side equals right side, both are completely fine. Okay, so this one we get from the Pythagorean identity, which we rearranged. And now we have left side equals right side, so we'll finish off our proof with left side equals right side and our little box or QED. Let's try another example. All right, so start by copying out the left side and right side. I'm looking through here to see if I have any ratios that are not sine and cosine. And in this case, it's already in terms of sine and cosine. So I'm going to move to working with the more complex side. So I think we'll start with the left-hand side here. And I'm noticing that eventually on the right-hand side, I'm hoping that there's no sines left in that, right? I don't really see any sine x's on the right-hand side. So I'm probably going to have to use an identity for sine squared that gets rid of sine squared and turns it into something to do with cosine. So let's take a look here. I'm looking for something with sine squared that I can replace so that I have cosine. And here's my identity right here. It says that sine squared x is actually equal to 1 minus cos squared x. So I'm actually going to replace sine x with 1 minus cos squared x. That's one of my rearranged Pythagorean identities. And then we'll move forward from there. So one thing that I really want you guys to look out for is I want you to think back to our rational expressions information. And some of you might be tempted at this point to cancel out one of these with one of the cosines on top. Now, this is a problem, and I want you to think back to our rational expressions knowledge to understand why this is a problem. Okay, look what we have next to cos squared and cos x. I can't cancel individual terms in a rational expression if they're next to sines and cosines, or sorry, if they're next to plus signs and minus signs, because I can't cancel individual pieces of a set of terms like that. So I can't cancel yet. So what else can we do? Well, I am noticing here that this is actually a difference of squares. It's 1, which is a perfect square, minus cos squared, which is of course a perfect square. So let's try to factor. This is going to factor into 1 plus cos x, 1 minus cos x. So you're going to see some of our rational expressions stuff kind of bleeding into some of our proofs in this unit. Okay, and you should be noticing something here. I now have all multiplication on top and bottom, and there's something similar on the top, and with the denominator here, I can cancel out a 1 minus cos x and a 1 minus cos x, and that's going to leave me with 1 plus cos x on the top. And that actually gives me something equivalent to my right-hand side, so I can finish my proof there by saying left side equals right side. Okay, so remember, you can cancel things as long as there's multiplication in between them. When you have individual terms that are being added or subtracted, don't cancel individual pieces of those terms. Okay, let's try one more. This time we're going to set up our left side and our right side. So just recopy, and I'm going to say leave a little bit of, make sure that your right side is kind of, or your left side here is kind of spacious. Leave yourself some space in between these terms. Just thinking ahead here. Okay, so the first thing that I'm scanning for here is I'm scanning all the trig ratios to see if they're in terms of sine and cosine. And I'm noticing one that's not. So this is actually what I'm going to start with, tan x. I'm going to use an identity that we used previously, and that is that tan x is equal to sine x over cos x. I use this identity a lot. So I'm going to replace tan x with sine x over cos x. And this is all over cos x. And remember, this is technically 2 over 1. So when I multiply this in, I'm multiplying 2 times sine and 1 times cosine. So let's get that top fraction simplified here. We'll have 2 sine x over 1 cos x divided by cos x. And this cos x technically has a denominator of 1. So when I multiply, or when I divide fractions rather, I will take the bottom fraction and I will flip and multiply it. Okay, so rather than cos over 1, we're going to have times 1 over cos. And then we'll simply multiply the numerators together and multiply the denominators. Remember, when you're multiplying fractions, you don't need common denominators. You only need common denominators if you're adding or subtracting fractions. So here we go. We've got 2 sine x over cos squared x. And now that I have everything in terms of sine x and cos x, and I don't have fractions inside of fractions, I think we can start working with our right-hand side here. So our right-hand side has 2 fractions that are being added. Now, our left-hand side. I'm noticing with our right-hand side here that it's one single fraction. I wrote plus here. That actually should be minus. Okay, so the right-hand side is one single fraction, and the left-hand side has 2 separate fractions. So it's probably a good idea if I find a common denominator here and I put this all together in one fraction. This was also on our list of tips and tricks. So each side needs what the other side has. This side will need a 1 plus sine x. And the other side is going to need a 1 minus sine x. Okay, make sure you multiply this into both the top and the bottom to make sure it stays equivalent. Okay, so let's merge this all into 1 now. We have 1 plus sine x minus 1 minus sine x, all over 1 plus sine x, 1 minus sine x. Okay, you will notice that I left some brackets here. That's actually really important when we're subtracting fractions or rational expressions, because the minus actually needs to go into both terms here. So we're just kind of recapping. Again, you see some of those rational expression rules kind of coming back into play here. So I'm going to distribute that, and then we're just going to gather all the like terms on the top. So I'm seeing here that we have a 1 minus 1. That's actually just going to cancel because that's going to make 0. And then we have a sine x plus another sine x. So if I have 1 sine x plus another 1 sine x, I have 2 sine x's. And this is actually great because I'm noticing over here that we have a 2 sine x on top, so we're getting close. I'm also noticing on the bottom here that we actually have a difference of squares. And usually in rational expressions, we don't expand those things when they're fully factored. But we do need to get somehow to cos squared x here. So I'm thinking that we're going to have to FOIL these out. So if I FOIL out this difference of squares, it then becomes 1 minus sine squared x. We used this in a previous proof as well. Okay, and we're super close here. I want the bottom to be cos squared x, and I have a 1 minus sine squared x here. So if you look back to our trig identities, you're going to see that 1 minus sine squared x is actually equal to cos squared x. That's a rearranged Pythagorean identity. So that's what I'm going to use here. So 2 sine x, and I'm going to replace this with the rearranged Pythagorean identity to make left side equal right side. And now that these are equal, I can say left side equals right side and end that guy with a box or QED.